I work for Splunk, and I work on OpenTelemetry. I help out with Java projects, and I'm the maintainer of OpenTelemetry Android. And what's in this presentation is my views and not necessarily those of my employer. Sometimes I look like that, so backup avatar. I didn't get these slides posted in time, so if you want to grab a link to the slide deck, now's your chance to do that. Very sky-level view of what we're going to be talking about. What's at risk, why you might want to encrypt your telemetry, how we can mitigate, and then some kind of close-up caveats, gotchas. We'll give 2 more seconds on that QR code. Okay, apologies for not getting that up in advance. All right, so hopefully most people who are at the Ollie Day track are familiar with OpenTelemetry and the fact that you would be able to instrument an application, have that sending telemetry over to an OpenTelemetry collector, metrics, traces, and logs. That collector will then receive that data, do some processing on it, export it to an Ollie backend where it will be visualized or further processed. And what we're talking about today is really this thing in the middle, and not the path out of the collector. It's really the path between your instrumented app and the collector. It's very typical to deploy an application, an instrumented application, and the collector on one host, even though here in this futuristic world, I'm not really sure what a host even is anymore. But oftentimes you will deploy these right next to each other, and that's pretty good. You know, you might have them talking on localhost, or you might have them talking through a Kubernetes network that's very tightly coupled. But often is the case, you might have a topology in which you have a collector that's sitting separate from your applications that are running on other hosts. And in that scenario, what we have kind of between them is a bit of network separation. And anytime you have this network separation, that brings up some kind of specific challenges for you. Specifically, that our friend, the evildoer, hacker, can gain access to your network. And that can come in a couple of shapes. In this case, there's a physical wire, you know, hanging off of this ridiculous network infrastructure. But that is still a thing that can happen. Physical access is a thing. And more often, there's some sort of network software access where a network system has been compromised, and that allows the attacker to have kind of full access to what's sent between peers. And as observability practitioners, you might be thinking, well, who cares about this? Like, why would a spy want to know what's in my spans, right? That's pretty boring. Just like seeing the timing of some like REST endpoint or like how many times a thing was invoked. Like, it's really not that important, right? Like, who cares? If you have looked at the OpenTelemetry project in any detail, you might have seen some example spans. This is taken directly from the OpenTelemetry project, where we have some spans, protobufs, converted into JSON so you can see what they look like. And certainly nothing exciting up here, right? A bunch of identifiers and some timing information. It's contrived, but this is what we have. So let's try it out. I'm going to pick one of the most basic Spring Boot applications that's out there. It's called the Pet Clinic. If you're a Java developer, you've probably heard of this. So you fire that up, and let's see what happens. Does anybody recognize what this tool is? Show of hands. Man, like 2/3, maybe more than that of the people in this room know what Wireshark is. Good, you came to the right talk. So Wireshark is a tool that lets you sniff on network traffic. Here I've highlighted packet number 9 in this very brief capture, and this is data flowing between Spring Pet Clinic and the collector. And it's kind of hard to see, but it's on an invocation of the post to v1 traces. So that's data going into the collector. And if you're paying a lot of attention, in the lower right-hand corner, you saw this block. And you start to see some ASCII characters in there that, when put together, start to form some interesting words. And so we're looking at the data content of that packet. And if we just rip that whole thing out and paste it into a text file, even though it's just protobufs, like literally it's binary, some of it is ASCII. And without even decoding the protobufs, we can start to see some interesting things up here. Like, oh, let's see. Something about KubeCon. See, my name is kind of in there. And like, we're not even trying very hard here, right? We're just like, oh, there's like Mac OS. Let's keep going. There's some path information. It's like like what version of, like where Java came from. There's like some libraries that might be on the class path. Hope log4j might not be in there. And then some stuff about databases, like there's kind of a lot this is one packet. This is like 10,000 bytes, right? So in case you were wondering, hopefully the alarm bells are going off already a little bit for you, because this is an information disclosure weakness. And on the surface, it might not seem that anything up there is alone very important, but attackers use this information disclosure and they couple it with other information to escalate their exploits or to find out more information about a target. So this is just an aspect of sending data between peers. In OpenTelemetry, the resources have attributes that are just golden. They give you all kinds of like service level and host level information. And then depending on which instrumentation you might use, the attributes that are up there are also golden for an attacker to sniff. So again, without even trying very hard, we've disclosed the host name, the OS and version. Based on the OS and version, you might go find some extra exploits for that host. The type of architecture, because some exploits only work on some architectures. And the PID, you might target the specific process if you gained access to that machine. The version of the JVM, we saw what database type we're talking to. And again, this is sent between your app and the collector, but it's information about what the app is doing. So it's even on the far side of the application. It's not sitting next to it. So the connection string used, which also discloses in some cases the database username, but certainly the host and port. And then all the way down to database level statements that show what tables and what schemas and what columns are being accessed or exist in that system. So, and that's just from one packet from one span, and we didn't even try very hard, right? We just pasted it, we didn't decode protobuf, and depending on what your developers have done, they might be disclosing lots more information on their tracing and their tracing model. Of course, your developers are able to put whatever they want on spans. They can put whatever they want on the resource in some cases. And if you're sending logs, there could be, sky's the limit. There could be anything in there. And so that, if you want to learn more about this type of weakness, it's covered under this MITRE CWE 319. You can read more about the reasons like why. If your spidey sense isn't already just like going wild, this will give you additional reasons like why you might want to be careful with this. Also, if you're in the US, which I think some of you are, if you're working with government contracts or in GovCloud, it states here, the information system implements cryptographic mechanisms to blah, 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 secure stuff during transmission. So you need to have encryption on the wire. That's part of FedRAMP SC8. And then some of you are also from the EU. So this ENISA and the NIS2 directive might be relevant to you. Those cover encryption in transit. GDPR, again, for people in the EU. And for people here in the UK, it might be the UK GDPR. And then the US HIPAA also has provisions that cover encrypting telemetry when it's in transit. Okay, so we've established, hopefully, that there's a problem. And we want to figure out what to do with it. And hopefully the answer is like pretty easy, right? We want to use TLS. Everybody's heard of TLS, right? Hopefully. That's our superhero. That's who gets to fix this painful disclosure problem for us. And if you've ever been on the internet, which you have, you know that when your browser uses HTTPS, when it sees HTTPS, it's using TLS under the covers. It used to be called SSL, hence the S, but yeah, April Fools, like your browser doesn't even show you URLs anymore, right? So maybe you don't know that, I don't know. Okay, latest version of TLS is 1.3. It's part of the IETF RFC 8446, and this is a 150-page document, which we can't read here because you all fall asleep and it'll take 4 hours. But definitely give it a read, like, on the plane or maybe before bed. Like, there's a lot of meat in here. It's very technical. We're going to cover just 3 short things from the intro. The first one is that TLS provides a secure channel between 2 communicating peers. That seems important to securing this. The server side of the channel is always authenticated. So authenticated means we're validating the authenticity of who it purports to be. And then confidentiality, once that connection is established, a TLS connection is established, what's sent over is only visible to those endpoints, so not visible to our attacker in the middle. Okay, so now we're going to configure our OpenTelemetry collector to use TLS. The collector uses a collector YAML file for its configuration. There's a block here that shows receivers, and that's the incoming side into the collector. And by default, it's using OTLP with a protocol of HTTP protobuf. And if you pop over to the README in the collector repository, you will see a section down below under advanced configuration. And one of those advanced configurations is TLS and MTLS. One kind of small word of caution, when you click that link, you will go to another document which describes TLS settings for both client and servers, so for both exporters and receivers, and they're kind of mixed together. Don't make the mistake of using the wrong configuration directive when it's not appropriate. The shortest kind of configuration that you care about here are these three things: the minimum TLS version that you want to support, and then the two files which are required to establish TLS connection with a peer. If you have older clients or you need to support older agents or older versions, you can bump that down, but 1.3 is often considered like the newest and you should try and use it. There are still plenty of people using 1.2. All right, so we've put that in our collector YAML. We fire up the collector. Oh, sorry, before we do that, there are additional, like if you're under FedRAMP and you or trying to get FIPS compliance, you might need to constrain which cipher suites are used, which algorithms. So you can find out what are available through the OpenSSL command, but you can list those here as well. So let's fire up the collector, get this working. Oh no, the collector doesn't start. Because we just threw some text into config, we didn't actually make those files, right? So how do you make a CRT assert file and a key file? Like, where would one get those things? Well, like all things, you have options. If you have a wallet and you want to spend some money, you can buy one. There's some limitations to that. You probably need to put your collector on the internet. It might need to be publicly available if you want to buy a cert from a public entity. In medium to larger size organizations, there are dedicated staff who manage certificate authorities and networks for your company, and they will often be able to generate a cert for you and install it in a collector for you. So basically your friend gives it to you. And then the one we'll talk about briefly here is generating it yourself and some of the challenges that come up from that. So OpenSSL, again, SSL being the predecessor to TLS. OpenSSL is a very common tool for generating certs. It's available on your system right now. I'll go over just very quickly what these command flags do. The REQ says, hey, OpenSSL, I want to request information about a cert. And then the very next thing, this X509, says, psych, I actually want to generate a cert. So this is hilarious to me, like the fact that you like request information but don't actually just generate one. And I'm sure there's some interesting history. If you know the history of this, come see me after because I think it's hilarious. Anyway, no inc is something that you would not want to use in production. What that does is it says don't put a passphrase on my key file. So normally you'd want to have a passphrase on your key file. For development purposes, we're going to skip over that. So days 365, that's how long before the cert expires. And then the next section with new key says, make me an RSA key that's 2048 bits long. There's some other information here that is attached as identity information in that certificate. I actually don't know what all of these fields are, but there is like the O is the organizational unit, L is some kind of locale information, C is probably country, and then common name. And the common name here is tied in with the additional extended field that we're adding, which is for DNS of localhost. I think when testing locally, if I didn't have that, it didn't work right. So, and then the two files that you want to generate, right? The collector key, the collector cert. All right, if you are working on FedRAMP or FIPS compliance, you might fetch a version of OpenSSL that has this FIPS extension enabled. By default, like on the Mac, it certainly does not. You might have to compile it yourself or find a Docker image that has that. But what that will do is it will constrain which algorithms are available to you to bake as compatible with your cert. And you can just add that with the dash provider FIPS and that will be enabled for you. All right, we're on track. All right, so now that you've generated those 2 certs, we fired up our collector again. Homer's happy, it didn't crash. We're going to test out that TLS is actually working by running OpenSSL again, but we're going to use the client command this time to connect to 4318. And we see that we got a TLS 1.3 connection. There was one of the certs, one of the ciphers that was chosen for us, and some other information here, our bit depth that we chose, and then some interesting bits down here. It's like, well, it verifies, but with this weird code 18 that probably isn't great, and it's because you're self-signed. Okay, fine. Well, I don't know what that means, but let's try it, right? Let's try it again. So we go back to Pet Clinic, we're gonna fire this up, and we're gonna see what that connection looks like. And we need to change our Java side, and it's a 1-character change. We change our OTLP endpoint from HTTP to HTTPS. Awesome. And then Java does what Java does, and it shows you a stack trace. And then you're like, no, I just want it to work. I just want to talk SSL to TLS to this thing. And the short summary here is that it failed, and it failed because it was unable, this phrasing is hilarious to me, unable to find valid certification path to requested target. Which kind of like certification path, like it's not trying to read the certs, the collector's reading the certs, like that's weird. But we'll come to understand why, and it's terrible and awesome at the same time. But it is a good thing, right? Like Java should not have just arbitrarily accepted whatever cert popped out of that collector. Like we just made that. Like why should our good friend here trust that? And he's saying, hold up. This collector gave us this cert, but we have no way of knowing that that's actually from who it says it's from. So I'm just gonna crash, right? And keep in mind, in our network separation, we have our attacker in the middle, and they have the capability then to generate whatever cert they want. If they want to pretend to be cncf.io and just like return that cert and inject that, then they could, right? So why would a client automatically believe that cert? And they don't, right? There's a chain of trust. And that chain of trust is a component of a cert that causes the client then to trace back back to a root authority. So with each step, there's an issuer. The issuer says, yep, that was issued by somebody that I trust, and that chain of trust goes all the way back, and eventually, hopefully, we end in a root CA. Again, for this to happen kind of in the public web, you typically pay for this, and we can verify that this chain of trust happens by running this SSL client again against the real cncf.io, and it will tell you at depth like 2 and 1 and 0, so you backtrack right here. We start with cncf.io, and it says here, cncf.io, its issuer is Let's Encrypt. So it pops up to Let's Encrypt, and Let's Encrypt says, yep, cool, I like it. My issuer is the Internet Security Research Group, and they are a root x1 authority. And it verifies that, and all is happy. If we do the same thing with our self-signed cert, we just have this one little hop here, right? And there's no real, like, I don't have an issuer because I just made this. I didn't put one in there, so that's why it's flopping, right? This is why it's painful. And yeah, you can go to, there's a lot, like this is a very complex topic, and there's like trust is a very complicated issue, right? Especially nowadays. But so we're just gonna blah, blah, blah over this. Well, hopefully, we saw with CNCF, like that they're using Let's Encrypt, and I think most people are probably familiar with what that is. It's awesome, like I use it all the time, but you're not gonna use it on localhost, and you're not gonna use it for internal hosts that might be on a VPC. You're not gonna use it for ephemeral hosts that flap up and down all the time. Like it's not for that. It's hard to make it work with that, and it's not what it's intended for. Because this is our application, we wrote it, we're deploying it. It's our collector, we own it and deploy it. We should be able to trust ourselves. And I hinted at this deployment model before, but it's what a lot of organizations do is they run their own CA. And they either deal with a server or they have some sort of like policy that's pushing CA certs out to individual hosts, or it's part of your deployment model, deployment pipeline in some capacity. And those are owned by like really smart people that manage that, right? Like that's a job. Like people do that. And maybe some people in this room do that, I don't know. But they will install those certs into an authority for you. They will make sure that those key files are available to your collector and whatever that automatic mechanism looks like for your deployment. And then when those are issued to a client, in this case Java, the issuer on that cert will say, yeah, I'm issued by ca.internal.corp, and then it's just a one hop, and in some cases it's just a local file. It's not actually a server call to validate that cert is acceptable for you. Okay. If you're on a Mac and you're a developer and you just want it to work, you're like, I made a cert, I plopped it in a thing, I want to make sure that I can talk TLS, you could throw it in your keychain file. I don't know if people use that, but I did once and it worked, so that's available to you. If you're a Java engineer, you can use the key tool, and key tool is something that ships with your VM and allows you to import certificates into your CA certs for that JVM. This is what the syntax looks like. The name there is not super important. The file, of course, is. You have to have the public cert. And typically, for Java to know about this, you put it in libsecurity CA certs. Okay, so we run that, and it succeeds. And then we try it again. It's getting very exciting, I know. So we're going to we're going to run Pet Clinic again, and then we're going to fire up Wireshark. And yay, there's what we see. A bunch of gibberish, right? This is just the encrypted payload. So I think this did what we intended it to do. Even though this is on localhost, it would be the same thing on a real network. You can't discern these two colors. There's client data at the top, there's server information at the bottom, and none of this is really legible. And that's what we wanted. So just to sort of wrap up, definitely some gotchas and caveats. I'm not a security expert. I'm sure that there is some aspect that you will tell me that I missed, and I appreciate that, so please do. When you set up TLS, it of course isn't free. Like anything we do, if you add capability, it will incur higher overhead. What that is and how it impacts you is gonna vary on your environment. I've said this a couple of times, but really setting up infrastructure for certificate management is a real challenge, and people do this and it's tough. And you can't, as a developer, you can't just kind of casually walk into this and expect to deploy it at scale in production. Like it's really hard to handle these things correctly. As I was writing this talk, it occurred to me, like, why can't, like, I think people want to be secure by default, and like efforts like Let's Encrypt, and it's become, like, every website now has TLS enabled, just kind of out of the box. Why can't we do that in OpenTelemetry? Why can't we just have TLS on by default? And hopefully some of the authority problems that I've outlined here kind of hint why that's not easy for us to do. But it also occurred to me that we use 4318 as like the default, clear text port, but maybe there's some possibility for us to specify an alternate port that kind of hints that TLS is in use, and there might be some benefit to that. Because in your browser, right, it's like 80 for clear text and was it 465 for TLS. So like if there were a convention on the OTLP side, that would be probably pretty cool. And then this talk is pretty fast. 25 minutes is all we get, so have to gloss over some stuff. Like there's no way for, in our current setup here, there's no way for the collector to verify that the client is who it said it is. And therefore, it could be receiving data from anyone. And so check out MTLS for more. There's some information in the collector docs about that as well, but MTLS can help with that. There's ways to put certs into the client code that will be sent on request. So wrapping up a little bit there, I can do a time check. We might have time for some questions, which would be cool. Yeah, I think we have 5 minutes for questions. That's cool. Or maybe not, actually. I don't know. That QR code is for the feedback, and feedback is welcome, so thank you.